Hello everyone. Today we will be presenting our material balance project, which is production of hydrochloric acid. This is our team members, which is Project Director Imran Azmi, Technical Lead myself Roh Nazwan, Project Manager Nur Afifah Dayana, and Documentation Lead, which is Robin Yusuf. So for introduction of hydrochloric acid is the aqueous solution of hydrogen chloride gas and the main component of gastric acid, an acid produced naturally in the human stomach to help digest food. Hydrochloric acid is synthetically produced for a variety of industrial and commercial applications. Hydrochloric acid is a strong corrosive acid that can be used industrially to process steel used in the building and construction industry. It is used in the chemical industry in the large-scale production of vinyl chloride used to make polyvinyl chloride PVC plastic, and it is one of the chemicals that is used to produce polyurethane foam and calcium chloride. Hydrochloric acid is also used to make many other chemicals and as a disinfectant and salicylic, a chemical that prevents the growth of slime in paper stock. Other common end uses for hydrochloric acid include household cleaners, pool maintenance, and food manufacturing. So this is the method that we use to produce hydrochloric acid. The feed material is carbon tetrachloride, and the production per annum is 1 million tons. So the method we use is fluorination of carbon tetrachloride.
So for today I'm going to talk about hazard treatment and precaution for our units. So let's start with the first unit, which is reactor. So the hazards are handling of HF, hydrofilic acid, a highly toxic and corrosive gas, a risk of heat generation due to exothermic reactions, and leaks or spills leading to HF exposure. The precaution are use corrosion-resistant materials like Teflon or Histolite for equipment, and provide detectors for HF and ensure proper ventilation. Moving on to gas liquid separator, the hazards are release of toxic gases such as HF, HCl or byproducts, high pressure hazards due to gas accumulation, and potential corrosion of the separator. And the precaution are use pressure and level sensors to monitor operating conditions, provide access to an emergency shutdown system, and use materials like stainless steel or lined vessels to prevent corrosion. Finally, absorption tower. The hazards are tower closing or excessive pressure drop, potential contact of acidic vapors with workers, and handling corrosive liquids like HF and HCl during absorption. The precautions are you equip the tower with a pressure relief valve, use neutralization system to absorb acidic vapors, and install corrosion-resistant packing materials inside the tower. For overall system, the hazards are leakage or accidental release of toxic gases such as HF, HCl, and exposure to high temperatures or pressures in the system, and slips and spills from corrosive chemicals. The precautions are conduct regular inspection and maintenance of all equipment, provide comprehensive training to operators on handling hazardous materials, and install emergency alarms and gas detectors throughout the planet. And finally, emergency protocols. For HF exposure, immediate use of calcium gluconate gel on affected areas, evacuate and seek medical attention immediately. And for HCl or NOH spills, neutralize with suitable agent like sodium bicarbonate for acids and dilute acids for alkaline spills. And use spill containment kits. For gas leaks, evacuate the area and activate emergency ventilation, and use CSPA for rescue operations. So that's it from me, guys. Thank you.
This is our overall body flow diagram. The units is reactor, gas liquid separator, and absorption tower.
Now for the calculation of reactor. So the DOF is equals to 0 because we have 5 unknowns, 2 reactions, 5 species, and other relations such as fractional conversion and selectivity. So for the assumption, we have 300 mole of basis. Now for the calculation, we use the fractional conversion of CCl4, which is equals to 85%. Then we will get the N2 of the CCl4, which is 15 moles. So using the selectivity also, we can get for the N2 of CCl3F form. So by that we can use the extent of reaction to have the other N moles that coming out of the reactor. Now by using the extent of reaction, we can also use to calculate the other mole that is coming out of the reactor. From that, we can have the mole that exists of the reactor, such as the CCl4, HF, CCl3F, and CCl2F2, and also the HCl.
In this gas-liquid separation process, we aim to separate a mixture into distinct gas and liquid streams, with HCl recovered in the gas stream as a final product. Let's begin with the input stream labeled as stream 2. This stream contains a mixture of CCl4, CCl3F, HF, CCl2F2 and HCl with a total of 300 moles. From the mole fraction, we know that 34% of the mixture is HCl, which corresponds to 102 mole. The separator operates under 25 degrees Celsius and 1000 mm mercury, acting as condenser. Under these conditions, only CCl4 is assumed to condense completely into liquid and exit as stream 3. As stated in our assumption, using Anton's equation constant, we can validate that CCl4 condense at this temperature and pressure, while the other components remain in the gas phase. This means the remaining substances exit through stream 4. Based on the separation of HCl remaining in the gas phase in terms of mass, HCl contribute about 362,777 grams in stream 4, accounting for a mass fraction of 0.9879. This confirms that HCl is major product in the gas stream. To summarize, we successfully separate and recover HCl in the gas outlet, achieving high purity and selectivity.
Here we have our absorption tower, which is a key unit operation in our process. It operates at a temperature of 30 degrees Celsius and 1 atm pressure. The main goal of this unit is to remove acidic and reactive components such as HF and HCl from the gas mixture by using water as the absorbent. And then we could get our final product. Let's start by going through the process flow. We have 4 main streams interacting with the tower, which is stream 4 is the inlet gas stream that contains a mixture of CCl3F, HF, CCl2F2 and HCl. Stream 5 is our water inlet stream, which serves as the absorbent in entering from the top of the column. Stream 6 is the liquid outlet. This is the water stream now containing the absorbent HF and HCl. Stream 7 is the gas outlet, which carries the unabsorbed gases, mainly CFCs, and a reduced amount of acidic components. So for the stream 4, this result is in total mass of 36,722 grams, dominated by HF given its high mole count and presence. Stream 5 is just pure water with 3427.9 moles, contributing a mass of over 617,000 grams. Then we get to stream 6, which is notice how both HCl and HCl appear in this outlet stream. They have successfully been absorbed by the water, demonstrating that the absorption process is working as intended. For stream 7, the gas outlets show what's left. From this, we can conclude that the absorption tower is highly effective at removing HCl and partially effective for HF, which is expected since HF is more volatile and slightly less soluble in water compared to HCl. So for the DOF is 5 unknown and 5 independent species balance, and that is 0 DOF. So it is completely defined and solvable.